All right, let's take a look at our graphic syllabus from the beginning of the semester and see where we are, how far we progressed. So we have gone through our multivariable function section, where we talked about it, and then we took derivatives, and then the gradients, and then we took double and triple integrals of these things. And so we've done this, our second type of function that we're dealing with. The first type of function that we dealt with was back here when we talked about vector functions, vector valued functions, where we studied parameterized curves. And then we took derivatives of them, and then we took integrals of them, where we modeled projectile type problems. We start with an acceleration, and we went to velocity and position by doing some integrals. So we've completed these things. Now our task for the rest of the semester is to focus on vector fields and parameterized surfaces. And then we're going to do the same thing. We're going to study them a little bit, and we're going to take derivatives and integrals of them. And today we'll start with an integral. Usually we start with derivatives and stuff, right? But this time we're going to start with integrals, and then we're going to backtrack and take derivatives of them. These things called divs and curls. And then we're going to go back and do the flux. All right, so that's where we are right now. And then after we get all this information done, we're going to take a look at the fundamental theorem of calculus to see how this thing relates. So next week is our first fundamental theorem of calculus. That's the fundamental theorem of line integrals, they call it. I call it path independence, but we'll see after that that they're going to be the same thing. They're going to mean the same thing. And then after that, another important fundamental theorem of calculus called Green's theorem. Now, when we study Green's theorem, we don't necessarily think of that as a fundamental theorem of calculus. And in the presentation, that may or may not come up. But we'll see when we tie this in with Stokes and Gauss, we'll see that it's really all just a version of the fundamental theorem of calculus. And then there's going to be one unifying symbol that represents the fundamental theorem of calculus. And that's really a cool looking equation that you might want to get a tattoo of that sometime. All right. So that's our little intro to today, and today we're going to talk about vector fields, and then we'll squeeze in some information about line integrals. All right, vector fields. I think my things got shuffled around here. So vector field. Now, we talked about transformations from 2 dimensions to 2 dimensions. We're going to formalize that and look at that from a different point of view. And we're going to take a look at vector fields in that way. And a lot of times we denote vector fields with a capital F just as the name. But, of course, just like y is equal to f of x, we can see that as b is equal to g of t or something different. Just the common symbol that we use. The thing that's important about the vector field is that the output is a vector. So we want to look at these vector fields as a vector function. Now they're different from our vector valued function because in the past when we have those vector valued functions, r of t, the input is just a one dimensional, it's a scalar. The input is a scalar t. Here, our input now is going to be a vector. And then our output is going to be a vector of the same space. So this is going to be our vector field. So how's that going to look like? Well, let me throw in a couple more symbols to confuse you. And in our example, we're going to go R2, but really this thing can happen in R3, so it can go from R3 to R3. So we can take, for example, our input variables x and y, and then our output variables would be another two variables. Now, I can just say u and v or something like that, but just to make it clear that we're taking a scalar function, I think a lot of times they call it f1. No, let me call it something else. P of xy, q of xy. Again, that's just a name. Instead of p, I could have left my f1 of xy and y1 of xy. But these are just scalar functions of two variables. So these are the functions that we've been dealing with. They could be as simple or as complicated as what might happen. So an example might be you have a vector field, and I'm probably going to start using parentheses later on, but for now let's just say it's a vector field. And here's a simple one, x comma y. X is a function of x and y is a function of x and y, right? Now in this case they just have one variable, but that's okay. Here's another example. Negative y comma x is it's a fairly popular example. I hope I did that right. Oh, God, this is minor, but can I just change this into y comma negative x? So let's start with those two examples. And as with a lot of functions that we've studied, when we first start studying functions, it'd be nice to get a visual of it. And so that's what we'll do. We'll see if we can get a visual of it. Now we have two numbers going in and two numbers going out. So if we think about it that way, those are 2 dimensions to 2 dimensions. It looks like this is going to end up being a 4-dimensional graph. And in terms of trying to go straight forward with that idea, it really will end up being a 4-dimensional graph. But the way we deal with vector fields is a little bit different. So if you know that something is a vector field, we're going to treat that a little bit differently from a usual graph that we've had. And so I'll first start by plotting some points, and then I'll show you how those points relate to the graph. And our graph will remain in 2 dimensions. So let's see. Let's make a table, because that's what we did when we first started learning about, graphing. Here it's just x and y, so I'm just going to rewrite x, y. It's kind of silly. And the thing to do is to put points in there. 0, 0 is going to be 0, 0, so it's not going to give me any information. But let's put 1, 0, for example, 1, 1, 0, 1. What is it? Negative 1, 1, negative 1, 0. Let's stop there for a moment and see what our outputs would look like. So if those are our inputs, our outputs would, in this case, it'll be exactly the same. So I'm just going to rewrite exactly the same thing. And let's imagine how this thing might look like. So, wait, this is called a vector field. What do you think of when you think of a vector field? If somebody said there's a vector field somewhere, what would you picture?
Water, like a stream.
What did you say? Little vectors. Yeah, I would have pictured little vectors.
Which is different directions.
Yeah. But a stream is another good example of a vector field. So when we're talking about a vector field, a stream is a good example of a vector field where the flow of water goes through. And then later on we'll talk about, have you guys heard of electrical and magnetic fields and stuff like that? So electrical and magnetic fields would be another good example of vector fields, and those tend to be visualized in 3 dimensions. All right, so I would be looking for a field of arrows, so that's exactly what we're going to do, a field of vectors, vector fields. So what I'm going to do is I'm going to first mark the point as a dot. And then what I'm going to do is I'm going to do this on my computer. So after I draw it, I'm going to move it somewhere more appropriate. So if you're drawing in pen or pencil, I don't know if it'll work for you. But I'm going to draw this arrow. If I have 1, 0, my output is 1, 0. And I want to look at that as a vector. So 1, 0 is a vector. I can put that in standard position, and that would be pointing to the point 1, 0. Right? But that vector doesn't seem like it's useful if it's just sitting at the origin. So what we're going to do instead is I'm going to move this vector so that the tail is at the point where it started. And if you do that, we can see that this is one of our vectors in our vector field. Okay? So we'll do 1, 1. Whoops, I don't want to turn that. We're going to keep that. So I'll start by plotting the point 1, 1 as a point, and then my vector is the vector 1, 1. Again, I'll start at the origin, but I'm going to say it's not useful just sitting at the origin, so I'm going to move that so that its tail is where that point is. Okay? So without doing the rest of this, can you imagine how this vector field might look like? What would it look like? It would curve? Okay. So imagine I have a bunch of arrows. I have a pocket full of arrows. And I'm going to put it on here. Put it on my graph. Will it curve up? Somebody imagining something different? Curving down? No? Should it?
It's all pointing away from the line x equals y.
Yeah, if we stay x equals y, let's try another point that's not on that line x equals y. Let's try 2, 1 or something. So what's your output? 2, 1. So the point 2, 1 is over here. The vector 2, 1, I always have to draw my vector at the origin first, and then I'll move it from there. So not necessarily along the y, x equals y line.
How can you draw the vector by putting it? It's just like going to whatever the point is on the origin.
Well, according to this, yeah. And when we do something different, it might look a little bit different.
Okay, but it's always just like that. Okay, we'll see. I'll see again.
Okay.
I'm not sure.
All right, well, that's good. No, it's good that you understand that you can't make sense of the question. That means there's more coming, that's why.
Yeah, yeah.
Yeah. All right. Well, I didn't quite get the answer that I was looking for. There's a lot of curvings and stuff like that. What? It looks like it's coming from the origin and exploding out. That's a good way to describe it. So this vector field is a vector field that just goes out like this. And the further you are from the origin, the longer your vectors are going to be. That's the other part of it. Okay? So that's what this vector field would look like. It's like an explosion. It's coming from, it's like a repelling force in the middle. It's just pushing everything away. Okay. So now let's take a look at this one, just to have a slightly different contrast from this first example. Let's say we have our x and y values, are the points, so we're going to look at them as points, and then our output will be not just the regular x and y like we had before, but it's actually y comma negative x. So let's see how this is going to look like. Let's just sample some points. You know how when you plot points, you plot 0 and 1 and 2 and 3. That's kind of like what we're doing here. Putting 0 in there will give you 0, 0 again, which is not going to give us a 0 vector. That's not very productive for us. But let's start off with 3 vectors. I was a little ambitious here, writing a whole bunch of vectors here. But let's just start with 3 vectors, draw it, and then we'll see if we decide that we'll try to find another vector. All right, so what are your outputs going to be? Your output, this is x is equal to 1, y is equal to 0. So what's my vector for this particular point? 1, 0?
Just get 0,
0, comma, negative 1. Right? 1, 1, what are we going to get? 1, comma, negative 1. How about 0, 1, what are we going to get? 1, comma, 0. Also known as 0. The number formerly known as 0. So let's put our points like 1, 0 right here. And let's draw our vector. Our vector is 0, comma 1. 0, comma 1. 0, 0, comma 1. That's this point right here, right? So I want to draw a vector from there to this point. But it's not going to be of use sitting at the origin, so I'm going to move it here. So that's one vector in my vector field. Right? Let's try to see where 1, 1 is. The point 1, 1 is over here. But what's the vector that's going to go to 1, 1? It'll be 1, negative 1. 1, negative 1. So from the origin, I would be pointing to this point 1, negative 1. But I don't want it sitting at the origin. I want it starting at the point where I left off, the point that we have. So then that's my other vector. Let's do one more. 0, 1. 0, 1 is this point over here. 0, comma 1. And then 1, 0 is a vector going from the origin to the point 1, 0. And so if I move that and place it where it's supposed to go, I'll have something like this. All right? Let's pause for a moment. And can you guys imagine how the rest of this vector field might look like? Well, he did something with his hand, too, that looked like he was right. What do you think it's going to look like? Circles. It looks like we're just going in circles here. You're going like this or something.
So I was waiting for you to just kind of subtly nod at whatever I was doing right, and then I say it out loud.
So it looks like it'll be circles, and it looks like it'll be circles going around. Actually, those. Undo. So when I was drawing those things, I was drawing kind of like paths of the vector field. But if I actually just want to see the vector field, I would just be drawing vectors instead of actual curved paths. So this is how the vector field would kind of look like. Okay? It turns out the graphing calculator program and a lot of other graphing programs, that 3D plotter also does vector fields. But let's take just a quick look at how this thing might look like to have it professionally drawn or technologically drawn. I don't know. This is the first one. Oh, can't graph that equation. What should it be? Oh, crap. I forgot how to draw vector fields here. What? YouTube. Carefully. Oh well. Probably. But now it's going to take more time. Circles, vectors, and differential equations, vector field. Oh, dx, dy. So the first vector field that we have is a vector field x and y. See, it's going from the origin and then goes out. The other vector field we had was a y and a negative x, which looks like it's going in a circular motion in the counterclockwise direction. Clockwise? Oh, I meant to do counterclockwise.
It's circular, not spiral.
Yeah, so it's circular, so if we follow a particular path, we're going to stay within the circle. It doesn't go out.
Or negative.
Would you graph on there the 2 cosine x and 2 sine y? Or just a circle radius?
Oh, I see what you're saying. Oh, x squared. And then I think this is one of these ones where I can grab the see a little vector. So at any point in my graph, I am going to have a vector in a specific direction. So that's what the vector field does for me. Oh, while we're at it, and since we have this program out, why don't we also visualize something in 3 dimensions, because these vector fields can live in 3 dimensions as well. So if we do that x, y, z again, x is x, y is y, z is z, then it's going to go out. But now it's going in 3 dimensions, so we can imagine these vectors.
Oh. That looks bad. Yeah, that's not
What about 4D?
We don't do 4D.
Added W in there.
And so if we make it go around in a circle, I think we had a y and a negative x here. It's hard to tell, but if you view it from the top, you should be able to see those circles. Is that the top? All right, I can't control. So you guys can mess around with this and see how these vector fields look like. But the idea is that a vector field is just a field with a bunch of arrows in it. And arrows are really just representative because they can't put an arrow at every single point because there's an infinite number of points, you know. So at any point that you pick in the field, there's going to be a vector coming out of there. All right? So that part is an important part. So that's a vector field. Examples of vector fields are what was your example again?
The first one or just all my other random ones?
The first one. Stream. So a stream, and let's make the stream a little bit more interesting, like curvy. So let's say this is a little piece of the river, and in general, the middle of your river has fast-flowing water, and as you go off to the side, your water doesn't flow as fast anymore. So I can represent that with smaller arrows, and then if you go right up along the bank, then your arrows will be really small. Still be going forward. So if you were to put like a stick to race with somebody else, have you guys ever played that game? A leaf or a stick where you put it in the water, you would probably want to drop it in the middle because that's going to send your vehicle faster through the stream than if you drop it off on the side. Now, of course, if it's in the middle, it may not all stay in the middle, depending on the flow of your field in that example. Yeah, it goes faster, so your velocity is faster there. You got a longer arrow on the merry-go-round, on the outside of the merry-go-round. Yeah. So that's that example. Another example would be like a magnet. If you just have or gravity. Gravity is a good example. And this is in 3D. How do you spell gravity? So this is the center of mass that we're talking about, and gravity pulls you down. So that's a vector field. Of course, we have to look at this from far away, like, so that we can actually make sense out of this. But if you're just within the atmosphere of the Earth and you're like hanging out in the moon and watching somebody drop somebody else off in the atmosphere in Earth, then the gravity is going to pull you down, and then at some point you'll hit the Earth. So that's another example. Magnets. I don't know how magnets work. But there's some magnetic field that would make something move from one pole to the other, and so you can imagine a vector field going around this, and then you also want to imagine this being in 3 dimensions that wraps around like this. So here we're looking at a cylindrical kind of shape of vector fields going in a specific direction. Okay? So those are vector fields. All right. Now let's take a look at a line integral. I guess before we take a look at a line integral, let's take a look at let's just take a look at a line integral. All right. So a line integral I don't want to just give you the line integral. I want to talk a little bit about it. Maybe I'll just give you the line integral. What the heck? So a line integral looks like this. A line integral is an integral where you're integrating a vector field over a curve. Yeah. So this dot, I made it big, and I want to make a point that this is, in fact, a dot product. And if you look at the f, you look at the two things that you're multiplying here, the f is a vector, and the ds is also a vector. And the ds is going to be described as, this is where I'm at right now, with respect to the tangent vector. Okay, so I'm kind of going backwards here. Normally I would like to look at a specific application or look at the scenario and then build the integral. Right here I just gave you the integral already, and we're going to work backwards and try to see what this actually means to us. So what does that mean? Imagine that we have a vector field. So I'll draw my vectors in red. And then imagine now that your curve C is some curve on that field. And for this particular scenario, and when we're dealing with integrals, line integrals, the direction, the orientation of the curve is going to be important. So yesterday when we talked about path integrals, I mentioned that it'd be good to start getting used to drawing the arrows on your curve so that you know the direction. Even though in the path integral, the orientation doesn't matter, the direction in which you're going doesn't matter. But for a line integral, the direction will matter. So here are our components. We have a vector field F, that's in red. We have a curve C, that's in green. And now we have to somehow translate this into something that would work for us, into a working definition where we could actually work with this integral. And like we did before, when we had a curve, we have to find a parameterization. So let us let R of t be a parameterization of the curve C. And then here we also want to say, just to give ourselves limits, we're going to go from A to B. So this is a lot of times this is introduced in a context of work, and when we get to deal with vectors, work is just a dot product of a couple of vectors. So the idea here is that if you have this vector field and you're trying to push something along this curve, what is the work done to go from point A to point B along this curve? So that would have been the application that I should have started with when we start talking about line integrals here. So that's what we're going to do, is we're going to imagine we're going to look for work. Now, what we have here is to find the work that goes through along this path is going to be a dot product between the path and the vector field. Now, saying the dot product between the path and the vector field seems a little too vague, but what I'm going to do is I'm going to focus on a particular point. Let's see, let's go over here. Just randomly selected a point. And if I want to represent a vector, if I want a vector that represents a path, what can I think about as I'm sitting on this point R of t here, R of t1, let's call. What would be a good representative vector for this curve at that point? The tangent vector, r prime. So that's what we're going to do. We're going to start off by looking at r prime. So at that exact point, you're moving in this particular direction, r prime. So this is r prime of t. Maybe that needs to be blown up a little bit. So let me take a look at this. This vector is r prime, which is describing the direction that you're moving, right? Now, there's another force that's pushing you in a certain direction, and that's the direction of the field. Now, I said if you're talking about a vector field, at every single point on that field, there's going to be a vector that describes that field. So more specifically, if I want to be at this field right here, at this point, there's going to be a vector that's going to be describing the direction of the field. So whether that be a flow of water or the flow of the electricity going through, this has something that has to do with the field. And so this is based on the field at that given point. So the point itself, I can describe the point as r of t, and then this is the field at that point, and then this is the direction of your particle that's going along that curve. This is the direction that it wants to move. So the work done at this exact the work done at this exact instant is going to be the dot product of these two things. So the work is equal to the dot product of this vector field vector. It's evaluated at that point, so we know that we're talking about this particular vector and not any other vectors out here. Right? We're talking about this particular vector, dotted with the direction that you're moving, r prime of t. Now technically this is t sub I, but what we're going to do is we're going to find the work done at every minuscule part of this curve. If you imagine partitioning the curve with delta t's, then this is what we're looking for. So really, this just gets wrapped up into this Riemann sum business again, and we're going to add up a whole bunch of them from the beginning to the end over here, from t is equal to a to t is equal to b. And then we have our working definition for this line integral. So the line integral of a vector field over a curve is going to be given by, provided that we have a parameterization for the curve using R, this is going to be the integral from A to B of your vector field evaluated at each of those points through that curve, through the parameterization R, dotted with R prime of t dt. All right? So let's take a look at an example. Let's pick an example from your homework. What? Oh, the labs are due on Monday, right? Yeah. And the homework's going to be due the Sunday of that.
Mother's Day.
Oh, there you go.
Your mom, here's your Mother's Day present. I finished all my homework.
All right, this is 16.2. So just to take a look at the difference in their notation, in the beginning they do this. Now the ds over here that they have is not bold-faced, so we want to think of that as a path integral. There's a function here, and then there's a space. There's no official dot, so it's not a dot product. It's just a regular multiplication. So this is a path integral. And you can distinguish that in the textbook from a line integral by looking at, where's their integral? By looking at this. This is an f dot dr, so their dot is really significant. And the r is bold-faced to let you know that they're actually doing a line integral. All right, so number 5 is a good candidate. Let's see if the other one. No, let's do number 5. Oh, here's number 6. So here's our example. We have a vector field that's e to the x minus 1 in the power in the I direction and xy in the j direction. And then we have this r of t. So in this case, they gave us the path. We don't have to come up with a parameterization for the curve. It's already there. So this is our path integral that we want to compute, and according to the working definition, I should be able to come up with an integral from a to b of f evaluated at r of t, which means I have to put the t to the 4th in for x and the t cubed in for y into my function. And then I would dot that with the r of t, I'm sorry, the r prime of t. I had prime, right, in the notes? Prime, yeah. dt. So if we do that, let's take a look at the different components that we need. We need f of r of t, which is f evaluated. R of t is going to be t to the fourth in for x and t cubed in for y. So I have my vector field is going to be e to the x, that's t to the fourth, minus 1, comma, x is t to the fourth times y is t cubed. So that's my f function. That's the first part of my dot product. The second part of my dot product is the derivative, so I need r prime. So that's 4t cubed, comma, 3t squared. So I would dot those two, f dot r prime. So the dot product is the result for the dot product is a scalar. I would multiply the components. So it looks like I have 4t cubed e to the t to the fourth minus 1 plus I have t to the seventh plus 3t squared. And this is not a vector. This is a scalar. So I don't have i's, j's, or I don't have those brackets with commas in between. And this is what's going to go inside of my integrand with my limits. And that's it. So integral from 0 to 1, 4t cubed e to the t to the fourth minus 1 plus t to the seventh plus 3t squared dt. Okay? We don't have to integrate this, right? Now the first one is doable. It's like a u substitution. So that comes out clean, and then the others are polynomials. Clean. Any questions about this problem? Straightforward? Yeah. Okay. Now, your line integral doesn't always look like this. Sometimes they present their line integrals a little bit differently, and I want to show you how line integrals can be sometimes written a little bit differently.
For the dot product, wouldn't we multiply t to the 7 times 3t squared?
Oh, yeah. Ooh, yeah. You guys didn't catch that, huh? It's got Lauren. Lauren caught it. The dot product, I was supposed to multiply this and this. I ended up adding it. So this should have been a multiplication here, which makes our integral a little bit easier even, right? So this would be 3 t to the 9th. Yeah. Thanks. All right, now I'll put the dot, dot, dot. All right. Let me show you another form of this thing. Let me rewrite this, or let me just copy this. Let's take a look at this and break it down into its components, provided that this is in fact some x and y components. Or did I use P and Q or F1 or F2? PQ. Yeah. So let's take a look at F. Let's do this in purple. And imagine F was PQ, or I's and J's if you want. I think they use I's and J's a lot in the book. And so R has X and Y. And I'm getting a little lazy with my notation here. But X is a function of T, Y is a function of T, P is a function of X and Y, Q is a function of X and Y. Okay. But I'm doing some shortcut notation thing. So what we have here is R prime is going to be X prime, Y prime. So what I want to do is I want to think about this working definition of the line integral and see if we can just write it a little bit differently. Here we're integrating this from A to B. I'm going to generically put C back in there. And then we have our F function, which is PQ, dotted with the R prime, which is X prime, Y prime, dt. So you see how this moves so far? Okay, now let me get a little bit particular with X prime and Y prime and say, well, X prime and Y prime is like dx dt and dy dt. Right? And imagine if that dt was sitting out here. I know people always make a big deal about not thinking about these differentials as fractions where you can cancel, but let's think about them as fractions that you can cancel. So imagine that scalar dt being multiplied through, and then you just have a dx. So what we have left is a line integral in this form. And if we do this dot product, we'll have p times dx and q times dy. And what we have here is another form of a line integral, and sometimes this is more common. You'll see this more commonly in certain applications. And you have to look at that and say, I don't see any vectors, or I don't see any vector fields or dotting things like we saw in the original form. In the original form, we see this being dotted along, right? But here, we don't see that. They look like they're all just scalars. But the fact that this is all under one integral, and one part we have a dx, the other part you have a dy, then we should really treat this as if it was a line integral. So let me redo the same problem. I don't know if that's a good thing to do, but let's go back to that same problem. And let's use a slightly different approach to our computing this vector field by, or computing this line integral by looking at this as p dq, or p d, what is it? pq dx dy. So to see this in another light, you would see the integral actually written like this. So we're going to talk about that curve C. The curve is going to be given by this parameterization. But this is going to take my p function, that's e to the x minus 1, and multiply that by a dx differential, plus my q function, which is x times y, and then that gets multiplied by the dy differential. And so now this is a line integral set up. So this line integral here, you would, instead of seeing all this like we saw in the problem, you would see this, and then they would just describe what C is. So they'll say C is a curve RT is equal to t to the fourth and t to the third. Or maybe you might have to come up with this parameterization. Okay? So if you see this, then you're just gonna, we can think about backtracking to make it look like this again and then do the dot product. Or we could take it from here and just say this is P, and I want to substitute this with t to the fourth for x and t cubed for y, and then I'll multiply this by dx, which is just the derivative of this with respect to t. So I would look at this as going from 0 to 1. Those are my limits of integration. E to the x, that's t to the fourth minus 1. And now my dx is the derivative of this thing, which is 3t or 4t cubed. And then this will get replaced by t to the fourth times t to the third. That's x times y. And then my dy is the derivative of this, which is 3t squared. And then now it all just becomes a dt. So you'll see that the work is the same, right? Except you might see your line integral in a different form. And if you do see your line integral in a slightly different form, you can just, instead of translating this back to f dot ds, s with an arrow, you can just go from here and say, oh, these are pieces that are already broken up for me. I could just take advantage of that and then work with it from here. So we'll see that we'll get the same integral and we'll get the same result, except we started off with a slightly different form. Okay? Any questions? All right, so before class tomorrow, I want you to have done the lab for 16. Yeah, Monday. Before class on Monday, I want you to have done the lab for 16.3. Yeah, 16.3 and 16.4. Okay, so that'll get us prepared for the week, for the lessons for the week. So if you get that done, then the lessons would make a lot more sense as they're being presented. Yeah, 1 through 2, 3, 4.